Cities and USF Patel College of Sustainability. And this is Sheila Sullivan, your host. We have success with the bell siphon, and we know this has been a tough journey for all of us because it works. It's like the dancing, singing frog. You go, I swear I heard it dance and sing, and then when people come to see it, it goes ribbit, ribbit. But today it's working, and it wasn't working just 10 minutes ago, and we don't really know exactly what we did. We have a lot of theories about what we did. But I want to first provide the proof, the evidence that it is working, and then we will take it apart and look at, and do we have a tape measure? Because if we can actually measure something, that would be science. So we're going to take a look at that. It's filling right now, and it seems to be independent of the flow rate. Last week I was doing a lot of tests, and I thought it was flow rate dependent, so I was playing with valves all the time. No, it doesn't seem to be dependent on the flow rate at all. Let's check this out. So we have maximum flow rate from the pump in the tilapia tank, and it shouldn't matter how deep the water here is either. Like, that's not an issue. So it's because this rate is at max. According to the way this is working, we can never overfill this. It will not flood. So the theory we had before, that if you have too much water in here, you'll end up with too much water in here before the siphon starts, which then, so we have to keep the levels low. No, we can make this deeper, which is good for the fish because it keeps temperature temperature stratification layers. The bottom will be colder than the top, and then the fish can find the place that's the most comfortable for them. So that's a good thing, because you don't want shallow water here in Florida. Heat exhaustion can kill certain species of fish, and then cold kills others. Tilapia don't like cold, but that's winter time. Let them be able to move up into the warmer layers. If it's too thin, it gets all cold. So there's that element to this. Okay, it's filling up now. We've been stalling, biding time to let it fill. You can see that even as it fills, it is draining. And I thought before, it has to stop draining in order to fill. And that's why I was playing with valves, because duh, if it's draining, it ain't gonna fill and it won't collapse the bubble. And that turns out not to be true. There's a constant turnover, which is good because that aerates the fish. You wouldn't need the bubbler mechanism with this if it's constantly producing bubbles down there. So that saves you a bunch of some money. Goodbye air stone. That means goodbye air pump, which means goodbye electricity. All you need is for the water pump. That's a good thing. As you can see now, it is draining. So while I was doing that talk, I missed the event of the bubble collapsing. But you can see it rapidly going down. And that is what bell siphoning is really all about. It's flood and drain, or flood and ebb. Many ecosystems in the world are flood and ebb ecosystems. Whether it is seasonal flooding of rivers like the Nile, or it is the daily flooding and ebbing of tides, or it is just wave action, crashing onto a beach, putting oxygen there as it crashes onto the rocks like this, and then the waves dragging back and pulling the oxygen, pulling the water out, pulling more oxygen in. There is an adaptation that organisms have to flood and ebb. So recreating it artificially in the lab, in the greenhouse, is a good thing. Now let us look down here. We've had an ebb tide, so we're way down low. That means that any roots of any plants down here have become fully oxygenated as it rapidly went down. But now, suddenly we see that a bubble must have been created because it leaped up. Did you see that a second ago? Just whoop, like that. It'd be nice if we had a plexiglass model. Maybe we can make one out of plexiglass, or a PET bottle. Wait a minute, there's a thought there. Why not make the bell siphon out of a hard, rigid, clear bottle? And then we'd be able to see what the heck is going on, and we wouldn't be just dancing in the dark here thinking we know what we're talking about. Because I had theories about a vortex having to be created by a funnel-like mechanism, which would look like the drain in your toilet or your bathtub, and that would force the bubble down. And I had all these theories I was talking about, that our current setup, which is a pipe like this, had sharp edges that could cut the bubble and prevent it. Maybe that's all true. I don't know, because it didn't work this weekend, and today it's working again. But it's going up. Before we do the measuring, Sheila, let's go through one more cycle so we have the timing of it. So I'll actually be able to look at video. Video is a great documentary tool, you guys, because you get time, and then you can stop time, and that's going down. So it never actually reached that black mark that we made, but it did fill this up so that the plant roots we're definitely getting enough enough water, enough nutrients. So yeah, there it goes. Down it goes. And it goes down pretty rapidly. I think we just hit upon the exact right height.
Yeah.
By pure chance.
Yeah.
First thing you can do while this is draining is you could measure the stub underneath.
Okay.
That way we... Is it still going down? It is. So I
Yeah.
can't... Still going down. Still going down. Still going down. Now you can hear it going... It's slurping. It's slurping as it's pulling air in. That's exactly what it should do. And then at a certain point, it's going to slurp enough air in that it's going to stop the draining. Do you see any drain? You look down there and tell me when it stops or diminishes. I hear it still slurping. Oh, stop. And did it really stop down there?
Yep.
All right, that is the moment of truth. So it now bubbled. It created a bubble and stopped. That is T0. And from that moment, we could then calculate how long it takes. This video is now, I think it was, I'll have to check it. We'll have to let's go through one more cycle because I can actually see a clock on here, and then I can, you can time, do you have a watch timer?
Okay.
All right, let's do the old stopwatch there. Marvelous measuring tools.
Turn it on.
Not yet.
When it
When it, you'll want to, we want to measure when it starts to drain, which you'll know from when that starts going. That's when you hit start and then hit stop when it sucks the air.
Okay, it's
It started?
starting. Yep.
Okay. But it's still rising. That's the interesting thing. So it seems it starts draining first before it even fills, and now it is officially not yet. It is not yet. Not yet. It's good to have. We should have markings, gradations on this every couple millimeters. There it goes. It's starting to drain. How long did that take?
30 seconds.
30 seconds for that, and then count goes down to when it inhales air. And is it a lot more? Nah, it's pretty much the same. That's sort of strange, but I guess it's matching the flow rate and then exceeding it. Still draining. Still draining. Still draining. Still draining. Appears to stall, but can't be stalling. And it could be that at this point, it's fighting with this inflow. But it is now continuing. It's down, draining down, draining down. It's about to hit the air gap area, which you can see down there over my finger. And now it's starting to, it's pulling in air. What time, how long was that?
58 seconds.
58 seconds, a few more seconds until it completely fills with air, and then we'll get that pop when it jumps back up. I'll give you a time to put on the stopwatch. You'll hear me go now when it happens. Not yet, not yet. Now. How many?
That was 18 seconds.
18 seconds of burbling.
Yeah.
So it pulls air in for 18 seconds. And now let's see how many seconds for it to fill up. Did that stop when it did that? Yeah, as soon as we heard that burble.
You see the tilapia?
No, where is he?
Right there. Oh, he's in the corner.
Where?
Right there.
Oh, there he is. Oh, he's big.
Yeah, he's big.
He's very big. Oh, look at that. Hello, tilapia fella. I'm gonna eat you one day, like I did your brothers and sisters. But I've given up fish because it's conspiracy.
I know. Gosh, it's awful.
There's that movie.
I know.
And you got in on the class by the time you were done with that, or were we still having that conversation?
Oh no. I got right at the end of it. But I have seen the sound.
Yeah. Eating your own tilapia is the way to go.
Yeah.
It is still going, still going, still going, still going. Probably already started dumping. We'll have to get them to measure when. Somebody should be just measuring this, correlating it with this person whose camera is on this, putting it together into a video, and then marking it down in a notebook, which nobody uses anymore. And it's going.
Okay, so that was a minute 33.
Minute 33. We should do this one more time and verify that those values are close to one another. See if it is consistent. So you do start again when you said minute 33, or you just doing the reckoning? Okay. So what was the last time to drain until it got there?
I have to pull it up on my phone.
Yeah. All right. We call this reconnaissance observations. We don't have to take data. We just have to get a hypothesis. And then they can do the data and prove our hypothesis. And we can sit in an armchair somewhere in Berlin with a pipe and say, I suspect later scientists will have to prove my theory that light is the fastest speed there is. All right, so it's going down and it's beginning to... It's burbling now.
57 seconds. I think last time it was 58.
Okay, that's close, and that could be error. Just reporting error. And now we said it's about 18 seconds before it starts again, so... And it's still flowing down there?
Yep.
Oh, it stopped.
Okay.
Okay.
That was 16 seconds.
16, right. So we're in some variance, but within plus or minus. And now the filling, let's see what this is. Exciting days here at the Rosebud Continuum, when real science is being done. And of course, the real purpose of this is just to publish papers. And then go on the talk circuit at conferences and say, we've figured out something that's been known for thousands of years. And we figured it out again. Verifying the laws of physics still work in the 21st century. The idea that we're living in the Matrix is nonsense. No, actually, I just read a great article, and I reposted it, that if we were living in the Matrix or living in a simulation, there should be some artifact. It's almost there.
And now it's picking up slowly.
It's actually going faster?
Yeah, now underneath.
That's why we need video evidence of that.
Because it was lighter and now it's heavier.
And it should be, but it's still rising, so even though it seems like it's going faster down there, it's not exceeding the fill rate, which is very interesting, because it's still, you would think that these things would get into equilibrium, which may have happened, and then you're like, I don't see any change.
Yeah.
And that was my initial hypothesis last week. It must be that this is coming in faster than this is going out. But there it goes.
Oh, about minute 30.
Which is what we had last time too, right?
Yeah.
And the drain cycle you said was roughly 56?
18 seconds. Oh. Yeah,
18 was the bubbling. So let's see if that holds true again. And we'll pull this out. So there's a lot of real science that can be done. And yes, all this stuff is known for thousands of years. It's not like we don't know about these physics. It's just that most school kids don't get a chance to play with parameters. They don't get a chance to measure meaningful things that will impact them beyond getting a grade, getting the right answer. Here, there's all sorts of parameters to continue to manipulate, like do plants grow or do they die? Do the roots get flooded and drowned? Do they get saturated? Now it's sucking in and out.
Okay. Oh, that's when it's 48 seconds. That's 6 seconds left.
Okay. So there may be some variance. And now the bubble just happened.
Okay.
Or maybe I caught it too late. No, if I caught it too late, it would be even less.
Okay.
All right, well, now is the time to pull this thing and do the measurement. So we pull this out, and we see that it was lower
Yeah.
than the standpipe. And this has got to be fairly precise from the uniseal, from the black.
Okay. So it's like 2, a little bit like 3, yeah.
3 and not a half, 3 1/4.
3 1/4.
Well, we can pull it and see, because now we're not going to get any draining. In fact, this is filling up. So let's pull it out, or you can pull it out. I'll video. Note that we are using just a 1-inch, I think it's a 1-inch uniseal, and now it's all draining down there.
3,
What did you say?
It's like 3.5.
Turning around for recorded evidence. All right, so as you said, we are doing about 3.5. It's a little bit shy of 3.5,
Yeah.
actually. It is 3 and it's a little less than 3.5. These are 16ths, so it's 3 and 1, 2, 3, 4, 5, 6, 7. No, 3 and 6 16ths. I'm seeing 1, 2, 3, 4, 5, 6, 7, 6. 3 and 6 16ths, we'll call it. It would be tempting to say it's 3.5 because it's a round number, and we have messed up in humanity so many times trying to base our science on magic numbers and beautiful, beauty and symmetry. It's not that beauty and symmetry don't exist in nature, but they exist after nature. We come to appreciate beauty and symmetry. It's like if you thought pi, I'm not saying you, but if you thought pi should be 3 and not 3.1472841, whatever it is, then you'd be wrong. But those extra numbers, we can just shave them off. They're inconvenient. So, and what is E? E is 2. I don't know my math, but it's not 2. E, 2 point something. Somebody watching may know what E is or look it up. So all these values, these incredibly important values in nature, values associated with the golden mean, with the Fibonacci series, the spiral shells of the Nautilus, and the worlds of galaxies, they're not round numbers. I don't even, they were
Sacred geometry.
sacred geometry, but it's never round numbers. And if you're in inches and feet, which is what we're doing here, you're even worse off because that wasn't calibrated to anything in nature except maybe the king's foot, which could have been a big foot or a small foot, and so a foot became the foot of a noble person or a scientist. I don't know who used to look that one up too. We do know that the tracks leading to the launch pad for the space shuttle were based on the width of a horse's ass. That's been verified because the Romans based the spacing of certain tracks on the width of a horse's ass for the chariot wheels to get through things, and it got passed down in tradition. And so ever since then, people joke that critical scientific dimensions were based on an arbitrary decision in the past, the width of a horse's ass, the length of a person's foot. And that's why meters and centimeters and millimeters, not only because they yield falsely simple and round numbers, so they make the math easier, so make as many mistakes. I do believe that they're based on wavelengths of light, but I can't be sure, because even those aren't, it isn't like 1 angstrom or 1 nanometer is corresponding exactly. There's always little digits after that, decimals. Anyway, a lot of philosophical digression. Now we've seen it has filled again, and the filling, of course, immediately begins to spill over because there's no bubble. And that then means that the plants will drown in here because they have their roots in that deep water. That is the sole reason for the bell siphon, so you don't have to have valves and come in the morning or use a timer to open the valve, fill this thing up, flood the roots with nutrients, and then come back and go, oh, now it's filled and the plants are dying. Let's open it up and let it drain and pull air in, or putting little aeration stones. I should point out on that this is the opposite technique over here. Here, you do keep the roots flooded. And as you can see, the roots are perpetually in water. They should drown. The reason they don't drown is because we have air stones in here. Plants don't drown if they're given sufficient oxygen because their roots are always wet. And if the oxygen level is high enough, then the root just thinks it's wet and saturated with oxygen. If it doesn't get enough oxygen, it will drown, and anaerobic creatures will take over in there. So this is a flood system. This is not flood drain, but all the plants are doing well in the flood system. They're getting nutrients from the fish. It's going through the denitrification process here, and then it's going into the roots here. And you can see there's an air stone down there. See all those air bubbles? Vigorous air bubbling in there so that the roots don't drown. With a flood and drain system using a bell siphon, you are obviating the need for an air stone. And as I pointed out, we don't need this air stone down here or this, because we get the aeration from the drain itself. And so this is redundant and unnecessary for that big tilapia fish who's down there, who probably basks under that. That's probably why he hangs out down there, is to get maximum oxygen.
Oh, yeah.
From that. It probably tickles him. So here we have a flood system, and it would work if we put air stones in. Of course, having the bio balls, or the what do they call this stuff? Not perlite, but whatever this stuff is called. Anyway, this might impede oxygen from getting through the entire layer, so it's much better to draw the oxygen down through everything at once, and that's what this is doing. Obviously, we should be measuring this. We don't know how tall this is, and we did see that it never got higher than this little bit of schmutz that's on here, which is why the schmutz is there. And we should measure that schmutz, because if we know the schmutz, we know the level. But apparently this thing is working. So the entire length of this to the top of the cap is 6 and 3/4, 6 and 7/8. I think if you actually were to put a card there.
Okay. Yeah,
6 and 7/8. Then there's that schmutz. That's the critical height that it's getting. That schmutz is exactly 4 inches. No, not exactly at all. 3 and 3/4, 3 and 3 and 1, 2, 3, 6, 7. That's 8, 9, 10, 11, 12, 13, 16. 3 and 13/16, and then there's the height of this, which works for some magical reason. How high is that cut? That cut is about a half, 3/4 of an inch. And for some reason, that works. Let's see if we can make that magic happen again. The other thing I want to show, if you want to hold this a second, is that we are using the Uniseal. It's a lot easier than using this tapered thing here. So that you had to shave, because that was originally one of these, and that doesn't fit down there, so they shaved it and made it tapered so that it fit, and then they put silicone. That's more labor. Can be done in a pinch, and you don't have to worry with this design if it leaks a little bit, but Uniseal works really well. And what we want to measure here, if you'll give me the thing, is we did get the top of that. We also want to look at what the bottom was, because that may have an effect, for all I know, how much length of this thing it goes down. We need to record it all. It's a 5-inch piece, and the under part is at 1 1/4. As we said, the over part is 2 and 7/16, and then 1 3/4 or 1 1/4 down there. There is, of course, a good 5/8 of dimension for this. Do the math, but that was working, so that's our sacred figure until we figure out why it works, and then we could mess with these parameters, slide this down, slide it up, and that may happen to you. You may find that somebody pushes it down too hard and ends up like this, and oh, why isn't it working today? Or somebody pushes it down too low like this, and oh, why isn't it working today? And then you go, well, we have in our notebook a figure that says that down here it was working when this was 1 and, what did we say? 1 1/4?
I think so.
1 1/4? No. Yes, 1 1/4. So that's 1 1/4, and then up here was 2 and 7/16. All right. So if we're just replicating the reality that we saw, this should work. Now when I'm pressing it down, I could make mistakes. So we'll have to measure it again once it's in. So I press the Uniseal in, trying to be careful not to push that pipe down. Look down here, there is no draining, so it's okay. Pushing that up there, and yes, it looks quite correct at 2 and 7/16. And now, put the shroud over, sit it right there, and pray. Because science needs prayer. And we continue to pray. Dear forces of science, forces of physics, laws of gravity, friction, thermodynamics, atomic motion, dear forces of nature.
Lord Bell Siphon.
Dear Bell Siphon, please work. You are so big and we are so small. You are so wonderfully holy, with holes draining down into the tank. So may the water flow through the holy holes at a rate that exceeds the rate of ingress here. Now I'm beginning to worry. We haven't changed any parameters, except one. Do you know what that parameter is? That parameter is that we didn't put in a full bubble.
Okay.
When we put this shroud on, an equilibrium had been established. Water level spilling down, cutting any bubbles that go in there.
Okay.
No further air got in. I just put the shroud down on top, putting air that's already air on top of this where it was already flowing. I didn't push the water level down. There's no compression. There's no incentive for the bubble to collapse.
Okay.
And that is the problem I discovered last week. Yeah, everything is the same except that crucial startup variable.
Okay.
So, the solution is, now it's going down. The solution is to drain it all the way down.
And maybe turn the water off.
Now let it drain down. Then, I hope this is the solution. I'm going to get egg on my face and then I don't understand physics, and maybe whoever is running this simulation is just messing with us. This looks right. Press this in. Okay, looks good there. No, it's still not drained enough. That drain. This is still 2 7/16. So we're good. Now put that in there. Now measure this. I'll put the shroud on. Hope I caught it in time. Oh, there's a piece of, no, there. Assume that that's the way it ends up when it finishes draining. The water's all gone down and then the air gets sucked in. I may have put it on a little too late. It should have been that the vents were exposed. That would simulate the natural condition of the cycle. But we will see. We know it takes approximately, what did we do, a minute and what?
30 seconds?
30 seconds to fill?
Oh, a minute 30?
A minute 30. So we wait for it. The other thing we did not measure, which we can measure later, is how high is the standpipe off of the floor of the tank.
Well, because it kind of sinks in the divot, so
It's not literally the one.
yeah, flush, yeah.
Right. And I can't be sure that the distance from the uniseal is the real important one. It might be the distance from the bottom of here,
Yeah,
which is higher.
yeah, that's yeah.
I mean, if we're dealing with really sensitive parameters of whether or not that bubble collapses or not, this may not be optimal. It just works. I believe it is going down.
It looks like it.
It appears to be going down.
Yeah.
Thus, lending credence to the hypothesis that you must start with a full bubble, with a full column of air. Column as long as it would naturally be at the second part of the cycle.
I think you just died.
I just died.
You had 3 people.
Famous. All right, now in, and in a moment it should stop. 1,000. Yeah, and yep, stop. Okay. Are you good?
Okay. That was one pretty cool. But I started a little just kind of oh, I think I picked it.
That should be irrelevant.
Okay.
As long as it doesn't let more air in or more water out. The rotation along the z-axis. I'm curious. Oh, it already immediately started. So I'm curious, like when it starts, when it stops, or when is that, or when it stops, and when it starts. But I think we can safely say that this problem can be solved.
Yeah.
For all, for perpetuity.
How's the conference?
Oh, I haven't attended, and I should.
Yeah, me too. I was on my way out, but then they saw you and they're like, oh, for all the visitors. I know it looks like a great lineup, but there's no schedule.
It is.
There is?
You get it? I'll post it. I have it.
Okay. But I'm like, well, is this the real Al Gore? That's what I thought. I'm like, how hard is that?
I think this guy is Alfonso Gore, Alvin Gore, or
But hey, he's making
Albert, not Elvis, yeah.
Yeah, I remember that. It's holding some support.
I was doing science. Generally science. So I was just saying to you that the article from Scientific American says that if we were living in a simulation, there would be a signature. And computer scientists know when a simulation is running. They can tell from within the game by looking at clock speed, CPU. So you reach limits. So I was going to say a designer built this enormous elaborate game like Minecraft or World of Warcraft, but you never reach the edge of the world, like in 13th Floor, that movie, where they suddenly come upon like this void and there's just like lines, you know, like, oh, that's a method to live in a simulation. You'd never know there was a simulation, especially if it was built in a curved way where every time you got to the edge, you ended up on another edge.
Okay.
So curved space. So you would never know from inside this that you're living in a simulation.
Okay.
You would never be able to talk to the controller. It's like an avatar in your game. You can talk to you. You can't talk to, I mean, you could build it that way, but it's not the way it's built. But the clock speed, seeing how fast certain events can go before they reach their limit, no calculation in that simulation can go faster than the CPU speed. So many bits changing per second, right? And you have much faster clock speeds for better and better computers, but there has to be some limits. They said there must be then a way of seeing that artifact in our world. And can you think of one? The first paragraph, I was like, oh my God, we've been missing this the entire time. What's the clock speed for this computer?
The sun?
Speed of light. Remember Einstein determined nothing could go faster than the speed of light? He was like, why? What's the clock speed of the universe? Nothing can go faster, which means it has to be a simulation. Of what? Of itself, which had a clock speed of light speed. So in fact, it's its original reality and its simulation. There would be no difference.
Perfect parallel universe.
Yeah. The only thing that would be evidence that there's a real beyond the simulation is a dimension where things can go faster than the speed of light. That would mean that in that universe, the clock speed is even faster. And you can hypothesize an infinitely fast clock speed, which we then call reality, because it would contain all other simulations or bits of that reality. So we're living in some simulation where the clock speed is set to the speed of light, 2 times 10 to the 8 meters per second squared. But the nice thing is, he then says, if you're living in a simulation, evidence that you were truly in a simulation would also come from anything that came into the world that exceeded the speed of light, which would mean tachyons, which would be time travelers. So time travel would prove that this was a simulation. It also tends to prove that time travel is possible. This old thing of, what if the grandfather could have, what if I go back in time and kill my grandfather, I'm never born, I could never have gone back to kill my grandfather. Bullshit. You went back,